All right, welcome. We're going to talk now about hazard ratios and survival curves. And probably the best way to get into this is to look at an example first. So here's a table from one of the papers that we're going to be looking at, and you can see here hazard ratios. Let's break this term down. So a hazard typically refers to a bad event that's going to happen. And in the case of this paper, it's death. And we have all kinds of deaths. We have death from all causes, cardiovascular death, and non-cardiovascular death. But I should mention that the event that happens doesn't have to be death. It could be time to having a heart attack, or it could be something good, actually, like even time to being cured from a disease. But in this paper, we're looking at death, so it's a bad thing. Now, in the denominator, we have the word ratio. Edit that out. And the next half of this term is the word ratio. And what that implies is we're going to be comparing two things by dividing. We're going to compare one thing to another thing. And in this paper, we're looking at vitamin D levels. And we're looking at a bunch of groups. Right here, we got 5 different groups at different levels. We've got groups with levels less than 25, 25 to 50, 50 to 75, 75 to 100, and greater than 100. So we will be looking at the death rate in each one of these groups and comparing them by way of a ratio. And our denominator in these groups is going to be this group here, the one that is marked as referent. So that's going to be the one that has a vitamin D level that is greater than 100. So let's take a look at this group right here. And so we're going to be looking at the group in the numerator that has a vitamin D level less than 25, comparing it to the group that has a vitamin D level greater than 100. And we're saying that the ratio of the outcome, which is death, is 2.5 times greater in the group that has low vitamin D than the group that has high vitamin D. So it would seem here it's not a good thing to have a low vitamin D level. There are some subtleties to saying that it's 2.5 times greater. It really isn't, and we'll go into that in a little bit. But I think if you think of it that way in your head, you pretty much are going to understand what this paper is trying to say. So 2.5 times greater. This one here is 1.24 times greater to have a level that is 50 to 75 compared to having a vitamin D level that is greater than 100. However, we cannot forget to look at the confidence intervals, right? So here this is the confidence interval for this one, and it says that our point estimate is that it is 1.24, but the value could just as easily be 0.95 or 1.62, and what that means is it could actually be worse to have a vitamin D level that is 50 to 75, or it could actually be better. We don't know. Or it could actually be the same if the ratio was 1. Now, if you look at this confidence interval, it does not include the point of no difference in a ratio, which is 1. And so it's saying even at our worst estimate at 1.64, you're still better off having a vitamin D level of greater than 100. You're still more likely to die with a vitamin D level less than 25 compared to the group that has a vitamin D level of greater than 100. And so what they did for us here is they put in boldface any of these numbers that has a statistically significant confidence interval. That means the confidence interval does not include the number 1. In this case, 0.7. It's lower than 1, but the high end of the confidence interval is much less than 1 as well. In this case, 2.02, it's higher than 1, and the low end of the confidence interval is greater than 1. Now, the next thing that we should look at are survival curves, and here's an example of one here. And what you'll see on one axis, you have the survival probability. The probability goes from 0% survival, means you're pretty much toast, to 100% survival. Woohoo, you live, right? And then you got time on the other axis, and here it's called follow-up in months, so 0, 50, 100, 150. And so you can see with each one of these curves, your chance of survival is decreasing. Your probability of survival is decreasing. And again, we're comparing groups. And you'll see here that I've color-coded each one of these groups that we can compare them now. And the group that has a high vitamin D level is dying off, but it's dying off at less of a rate than the group that has a vitamin D level of less than 25. It's dying off at less of a rate than all of these as well. And so these are called survival curves, or Kaplan-Meier curves, named after the people who came up with it. And this is just a way to visually understand what's going on. Now, you might be asking yourself, and quite legitimately, what's the difference between hazard ratios and risk ratios? They actually sound very similar, but they're really not the same thing, and let me explain why. So let's say that we're doing a study over the course of over the course of time, and we're looking at two groups, one who is exposed to something and one who is not exposed. Then we decide we're going to take a look at the death rate of these groups. We're going to measure that over time. First, for the not exposed group, it looks like most of them die pretty early, and the exposed group seems to live a lot longer. They die more along the end. So when you calculate a risk ratio, you are looking at this entire time interval. You're looking at the risk of death in the exposed group versus the risk of death in the not exposed group. And we would calculate something like this, the number of dead over the total in the exposed, number of dead over the total in the not exposed, and divide them, and we got a risk ratio. Now let's look at how we calculate hazard ratios. It's just a little bit different in that we're going to slice this time interval up into different intervals. And we could calculate the hazard rate for each one of these intervals. So for this not exposed, we know that 4 of these people died of the 21, so about 19%. And the hazard rate for the exposed group, only 1 out of 15 died, and so that's about a 6% rate. And if you were to calculate it for the next interval, we got 1, 2, 3, 4, 5, 6 out of 17 that were alive after this point, 35% event rate here. And we had 1 person die in the exposed group out of a remaining 14 that were left, so about a 7% hazard rate. And you could calculate the ratios of these in each one of these intervals as well. And the thought is that the ratio between these two will stay about the same. That is, the hazard rates are proportional. So let's talk now about survival probability. If we look at one interval, let's say this interval right here, the survival probability depends on 2 things. It depends on the probability of surviving this interval times the probability of even making it this far. And the survival probability and the hazard probability are related by this horribly ugly formula, but don't worry. A computer will do that for you. You don't have to memorize that. We're just going to think about the concepts here. And so that there is a relationship between dying of this, or surviving. And it's a kind of an inverse relationship, and it's complicated because it's using intervals. And remember, if you made these intervals infinitesimally small, you would have an instantaneous probability. And now we're going into the realm of calculus, which is why you see funny things like this here. But we're not going to think about any of that. We're just saying that the hazard ratio is the ratio of one group surviving compared to another group within a specific time interval. And you can also think of it as a survival probability, which is the probability of surviving to this interval times the probability of surviving inside that interval. And if you graph all of these survival probabilities, that's when we get our Kaplan-Meier curves. So if we look now at this survival curve that I've drawn here of the exposed versus the not exposed group, one thing that you'll see is that this line and this line are diverging. They're going farther and farther apart because the survival in this group is getting worse than the survival in that. And remember we talked about that it usually is going to be, the hazard ratio is going to be a constant rate. It's going to be proportional, and that means this is going to be grow at a normal rate. Now this doesn't have to be the case, though. You could have one survival curve that first starts out getting worse, and then it actually starts getting better. So if you look at this part of the curve over here, the exposed group here has a less of a event rate. It's got a better survival rate than this part. But if you go down over here, the survival rate is worse for the exposed group and better for the not exposed group. And so this one does not have that proportional hazard rate. I only mention that because you're probably going to at some point see something where they talk about Cox models and Cox proportional models. And those models allow you to do things with confounding, using hazard rates and survival curves, but they really, really assume that the rate is proportional. And so it doesn't have to be the case, but it usually is proportional. And then you're able to use those models to deal with the confounding. So this is, in a nutshell, what hazard rates are. I'm going to review the points again. Remember, hazard ratios are not the same as risk ratios, but they're about the same thing, right? We're going to look at the hazard ratio, and we're going to, as a number, and if one group is 2.5, if the hazard ratio is 2.5, it means that in a particular given interval, one group has a 2.5 times more likely chance of experiencing the event, in this case death, than the other group does. It doesn't mean that the group in total is 2.5 times more likely, remember, because each one of these looks at particular intervals. But you can think of it like that, like it's looking at the whole time interval, that one group is more likely than the other group to be experiencing that hazard. That element of the time interval is important with the hazard ratios. And remember the survival curves. It's these little jaggedy things like this, the Kaplan-Meier curves, that shows you who's dying off more quickly than the other group. You can compare groups that way. And that's it for hazard ratios. If you have any questions, please put them in the comments below. Thank you for watching.